Okay, let's continue with constitutional isomerism. This question has a lot more constraints, but it's not necessarily more difficult. So let's see. Line angle structures for all secondary alkyl bromides with 5 carbon chains only, having the molecular formula for bromohexane, C6H13Br. Immediately, there are 2 important things to note. Secondary is in reference to the carbon in which the halide is bound. So the bromine needs to be bound to a carbon that's bound to 2 other carbons. That makes it secondary. 5 carbon chains only means the longest carbon chain in our compounds will be pentane. No butanes, no hexanes. So to bring the carbon count up from C5 to C6, we need to include a methyl group somewhere. That adds in the missing carbon. Write the IUPAC name for each structure. Again, we're only dealing with pentanes. This time we need to account for stereochemistry. So let's draw out the first structure here. Now we just mentioned that 5 carbon compounds will mean the longest carbon chain is pentane. So we draw out pentane, and then we need to include the 1 methyl group and the other halide substituent. So 2 substituents in total. So if we look at pentane, we can't include the bromine right here. Because if we do, and look at the carbon in which it's bound, it's actually primary. There's only 1 other carbon bound to the halide-bearing carbon. So this is primary, and we're not looking for this. Let's put the bromine right here. Let's call this carbon 2 and put the bromine right here. Because we need to account for stereochemistry, let's put it on a wedge. Again, it's arbitrary. At carbon 3, let's put in that methyl group. And again, arbitrarily put it on a wedge, just for now. The next step would be to identify the chirality at carbons 2 and 3. Remember what chirality means. At carbon 2, we have a bromine, a methyl group, a hydrogen that we don't show, hiding right here, and this sec-butyl group coming off towards the right. So if you have 4 distinct groups coming off of any particular carbon, it's considered chiral. 4 distinct groups. It's the same story at carbon 3. If we put in the hydrogen that's hiding, right here, and look at all 4 substituents, they are unique. Methyl here, hydrogen, an ethyl group coming off to the right, and towards the left, it's a modified ethyl group, a bromoethyl group. All 4 substituents are distinct, so carbons 2 and 3 are chiral. Now let's identify the chirality. Based on atomic number and Kahn-Ingold pre-log rules, we look at the substituents with highest atomic number or distinguish between similar ones based on first point of difference. Bromine takes first priority. Towards the right, this sec-butyl group bound to carbon 2 takes second priority. Then we look at the methyl, third priority, and lastly hydrogen. Connect the dots, bromine, sec-butyl, methyl. It looks like it's going clockwise, so at carbon 2 it's R. Now if we look at 3, we analyze priority in the same way. We look at ethyl and this bromoethyl. We know based on first point of difference that the bromoethyl will win out. So this group here, bound to carbon 3, takes first priority, followed by ethyl, then methyl, and then hydrogen. Connect the dots, 1 to 2 to methyl 3. Again, it's clockwise, so at 3, it's R. And then we name, as per usual, 2-bromo, 3-methyl pentane. Believe it or not, we've done most of the work. If we have 2 chiral centers at 2 and 3, that means we have 4 unique stereoisomers based on the 2 chiral centers, according to this little trick here. If we had 3 chiral centers, 2 to the third would be 8 stereoisomers for 3 chiral centers. We have 4 unique stereoisomers for these 2 chiral centers. So the name will stay the same, but we can play around with the chiral centers. For example, at carbon 2, instead of a wedge, how about dash? At carbon 3, instead of a wedge, how about dash? In this case, it's a wedge and wedge linkage. How about wedge, dash, dash, wedge, dash, dash? We have 4 different combinations that we can account for. So let's try one. Again, pentane is the longest carbon chain. Let's put the bromine on a wedge. Let's keep the methyl on a wedge. Sorry, put bromine on a dash. Keep methyl on a wedge. In a third structure, this time let's switch it up. Let's put the bromine on a wedge. Let's put the methyl at carbon 3 on a dash. The last combination is to put both substituents on dashes. We still haven't done that. So we put the bromine on a dash and the methyl at carbon 3. So we have wedge wedge, dash dash, dash wedge, wedge dash, 4 different combinations. Now if we look at the names for this structure, this one and this one, they're all 2-bromo-3-methyl pentanes, but they differ in terms of stereochemistry. So we determined that a bromine on a wedge in this particular case means R. If we put a methyl on a wedge, it's also R. So most of the work is done. That means a dash at carbon 2 is S, and a dash on carbon 3 is also S. It has to be the complete opposite. If you flip the stereochemistry from wedge to a dash, whatever you calculate for wedge would be the opposite for dash. That's why at carbon 2, this is S, and at carbon 3, this is still R, but this would be S. Again, we're using this structure as the benchmark. So to name this structure, it would be 2S, 3R, 2-bromo-3-methyl pentane. All right, the name stays the same. Right here, it would be 2R, 3S. And here, it would be 2S, 3S. Again, on the exam, always write out the full name. I'm just trying to identify the stereochemical differences. So RR, SR, RS, SS. Those are our 4 combinations. But we're not done here. There are other compounds as well with 5 carbon chains, but different kind of connectivity and stereochemistry. Again, let's start off by drawing just pentane. In the previous structure, we had a 2 and 3 linkage. What about 2 and 4? We haven't tried that. So let's put the bromine at carbon 2 and the methyl at carbon 4. Bromine on a wedge, and in this case, this is not a chiral carbon. There's another methyl bound to carbon 4. The only chiral carbon here is this one, because it has 4 unique substituents. We have a bromine, a methyl group, there's a hydrogen hiding in the back right here, and this isobutyl group towards the right. It also follows that we can switch the stereochemistry here and get another unique structure. So we draw out the 5 carbon chain, keep the methyl at carbon 4, but now instead of a wedge, we have a dashed bromine, which will be the opposite of a wedge. Now to name this, it would be 2-bromo-4-methyl pentane. If we analyze the stereochemistry, bromine takes first priority, isobutyl takes second, compared to methyl, which is third. Of course, hydrogen is last, and it's projecting into the back. Connect the dots, bromine 1, isobutyl 2, methyl 3, clockwise orientation, so it's R at carbon 2. So the final name is 2R, 2-bromo, 4-methyl pentane. That means this structure is 2S, 2-bromo, 4-methyl pentane. Now, so far, we have 6 different structures, 6 unique structures. We have 2-bromo-3-methyls, and we have 2-bromo-4-methyls. But we didn't account for putting the bromine at carbon 3 and moving the methyl to carbon 2. That would give us another unique constitutional isomer. We draw out pentane first. Let's put the bromine arbitrarily on a wedge. That makes it a lot easier to read. Let's put the methyl right here at carbon 2. Again, not wedge or dash, because this carbon is not chiral, but this one is. Now the drill is the same. If we put a bromine on a wedge, we can also put it on a dash, like so. Methyl goes to carbon 2. Again, this is a chiral carbon. All we do now is determine the stereochemistry. Bromine takes first priority. If we look at an ethyl group coming towards the right versus an isopropyl towards the left. Isopropyl wins out by first point of difference, so that would take second priority. Ethyl takes third. The hydrogen hiding in the back takes fourth. Connect the dots, 1 to 2 to 3, clockwise orientation, so it's R. 3R, 2-methyl, 3-bromo, pentane. And obviously this would be 3S, 2-methyl, 3-bromo, pentane.